In this video, we are going to talk about molarity and dilution. So starting with molarity is a method, a quantitative method that is used to describe the amount of solute, and this amount is usually expressed either in moles or grams dissolved in a given quantity of solution. And specifically, when we're talking about molarity, which is a unit of concentration, and sometimes we refer to molarity as the uppercase M right here, and it must be uppercase M because if you were taking Gen Chem 2, there is another concentration unit with a lowercase m, so we don't want to mix them up. And it is the SI unit of concentration. And molarity, when we want to express it or calculate it, it is the amount of solute in moles per liter of solution. And the how you express molarity is very important because it's moles again of solute over moles of solution. So note that solution is two components. Solution is solute and solvent. Okay. And molarity is also very useful because it's one of the popular units. You have hopefully seen it or will see it in Chem Lab. And with that being said, let's see how we can prepare a molar solution. So to prepare a molar solution, for example, this is how to prepare 1.00 molar of sodium chloride solution. So in order to prepare it, first of all, you'll need to weigh out an equivalent to 1.00 moles of sodium chloride, which is going to be 58.44 grams. And of course, this comes from the molar mass of sodium chloride. And then we have this volumetric flask, which is about 1 liter. And we are going to add the 54.88 grams of sodium chloride to it. And then we are going to add water to the solid and try to dissolve the sodium chloride till this etched mark. This etched mark indicates this is the 1 liter, and we mix it to prepare the 1.00 molar solution of sodium chloride. Now let's look at an example how to calculate the molarity of the solution if you are given the mass of the solute and the volume of the solution. We will also learn how to calculate the molarity of ions of this compound, which is sodium chromate. Okay, so it's asking what is also the molarity of sodium and chromate ion. So let's look at how we can perform this problem. Now, the first thing is I want to start with is calculating the molarity of the sodium chromate solution. So we have here, so we agreed that molarity is going to be moles, in this case of sodium chromate divided by liter of solution. Now note here that we're starting with a mass, so we will have to convert from mass to moles using the molar mass of sodium chromate, which is given to me right here. So I can say that it's 12.5 grams of sodium chromate, and here is times 1 mole. So I'm here dividing by the molar mass of sodium chromate. Okay, and from here, I should end up with the moles. Okay, and then divided by the volume of the solution. So the volume here is given to me in milliliters, but remember it should be in liters. So I will say that in 1 liter, I have 1,000 milliliters. Okay, and then we are going to look for the lowest number of sig figs. in this case, and the lowest number of sig figs is going to be the 752 sig figs, and in this case, I will end up with 0.102899739 molar. And if I'm rounding to 2 sig figs, is going to be 0.10 molar of sodium chromate. Okay. Now the next step is we can use now this value right here as a basis to calculate the moles, sorry, not the moles, the molarity of the sodium and the chromate ions. So in this case, we're going to use again the stoichiometric amounts, or the number of moles of the sodium and the chromate ions in one formula unit of sodium chromate. So I will call this step 2. So in this case, I can say that for each, and I will copy and paste this here. Okay. And I'm going to say, instead of molar, I'm going to say moles of sodium chromate in 1 liter. And then I will start with the sodium ion. So for every mole of sodium chromate, I have 2 moles of sodium ions. Okay, and this should give me 0.025799429 molar, or moles per liter, of sodium. And again, I'm sticking with the number of sig figs, so we have here 2 sig figs, so it will be 0.21 molar of sodium ions. Okay, now the third step is, okay, we're going to do the same exact way to calculate the molarity of the chromate ions. Okay, so for the molarity of the chromate ions, note that it is for every mole of sodium chromate, I have only 1 mole of chromate ions. So it becomes very simple. So you should make a prediction that you will get the same molarity as you got for the molarity of the sodium chromate itself. And I will show you. I will end up again copying and pasting the same thing. Let's move this up here a little bit, and then we will copy it and then paste it right here. And then instead of writing out here the moles of sodium, I'm just going to say there is 1 mole of chromate ions, and I'm going to get 0.10 molar. Of course, it's going to be this value. I'm going to round to 2 sig figs molar of chromate ions. Now, I want you to work on this with me and try to think now how many grams of carbonate ions I am going to have in 100 milliliters. So it asks for grams of carbonate ions in 100 milliliters of 3.47 molar of magnesium carbonate. Okay, so in this case, I can start with the 100 milliliters. Okay, and with the 100 milliliters, I can convert them to liters. Why? Because molarity is moles over liters. So I can say that in 1 liter, I have 1,000 milliliters. Okay, and then I'm going to start by breaking down this 3.47 molar. So it becomes 3.47 moles of magnesium carbonate, okay, divided by 1 liter. Okay, so we see now everything cancels out. Okay, and then finally, I'm going to say that 1 mole of carbonate ions is present in 1 mole of magnesium carbonate. And it wants the mass in grams, so I'm going to multiply by the 60.01 grams of carbonate over 1 moles of carbonate, and it's going to give me 20.82347 grams of carbonate ions. Now let's look for the lowest amount of sig figs. Looking here, it's 3 sig figs. So in this case, it's going to be 20.8 grams of carbonate ions. All right. Let's move on to the next problem, if you want to do it. How much solid in grams of potassium chromate is needed to prepare 0.250 molar of solution? Now, I want you to pause your video, okay, and try to work this on your own, okay? Now, the first step is I am going to, so it asks for solid in grams of potassium chromate and needed to prepare 1 liter of 0.25. Okay, so first thing is we need to isolate the moles, okay? And I'm thinking out loud with you, okay, from the 0.250. So let's break this down. So it's 0.250 moles of potassium chromate in 1 liter, and I want to isolate the moles, so I'm going to multiply with 1.00 liters, and I got here 0.250 moles of potassium chromate. Okay, now 3 sig figs. And this becomes easy because then I can use the moles right here and then convert them to grams using the molar mass. So I will take this number right here, and then I'm going to multiply by the molar mass, which is given to me in the question, the 194.19 grams of potassium chromate in 1 mole of potassium chromate, and this should give me 48.5475 grams. And lowest number of sig figs here is 3. Therefore, I have here 48.5 grams of potassium chromate. I hope this makes sense to you. And let's move on to the next aspect of, or next part of this video, which is how to dilute solution or dilution in general. This is another technique you're going to learn in lab. And this involves a very simple calculation, and this is related to specifically molar solution and diluting them. So let's learn what is dilution to begin with. So dilution is the preparation of a less concentrated solution, okay, from a more concentrated solution by adding a solvent. Okay, so the most important thing you want to focus on in the aspect of dilution is the number of moles, or the moles of the substance stays the same, is just the volume increases. And we can just look at molarity, right? So molarity, which is M, equals to moles of solute divided by 1 liter, or liters of solution, which is the volume. So this right here stays the same, okay? And this here increases. So if you know that molarity is inversely proportional to the volume of solution, the molarity goes down and the solution now becomes diluted. And for this relationship, we're going to use a very simple equation below here, which is moles in more concentrated solution equals to moles in less concentrated solution. We established that up here. Therefore, the initial molarity, which is M1 times the initial volume, equals to the final molarity times the final volume. Okay, or we can say that the concentrated molarity and solution equals to the final concentration of the diluted solution and the volume of the diluted solution. And I will zoom in a little bit right here to show you that if this cube right here with a length of 2 centimeters. Okay, so if we want to calculate the volume of the cube is 2 by 2 by 2, which is 8 centimeter cube, and we took 1 centimeter cube or 1 milliliters of this initial solution, and we added to just some solvent, my final solution will be diluted. So I will have the same amount of moles, but they're going to be spread over a larger volume. I hope this makes sense because molarity is very important and is going to be used throughout Gen Chem. This is again another example of how dilution takes place, and this is very cool because this is a colored solution. So you can even see here in the third image that we started with this blue solution that's dark blue, and what's diluted becomes a light blue, which is pretty cool. Now let's check our understanding or really look at an example of how solutions are diluted and how to perform these calculations right here. And we have here in this example a 61.08 grams of barium hydroxide. You're given the molar mass is dissolved in 1.800 liters of water to form a solution. And then how many milliliters of the solution must be taken to make a 1.00 liters of 0.100 molars of barium hydroxide. Okay, so it wants you to find, so if we are using M1 V1 equals to M2 V2, we want to label what we have or extract the information that we have from the question to be able to find exactly what we are looking for. Okay, so what do I have in the question here? I have the volume of the final solution, which is 1.00 liters. I have the molarity of the final solution, which is 1.00 molar. And I want to find, so this is what is the variable that I want to find here is the initial volume. And in addition, I'm given information to find the molarity of the initial solution. So let's find what is M1, starting with M1. So the molarity here is the moles. I'm not given the moles directly, but I can determine them using the mass of the barium hydroxide sample. Okay. Divided by, or not divided by. We are going to, it's divided by the molar mass. So barium hydroxide divided by 171.34 grams of barium hydroxide. Okay, divided by, so this now here gives me the moles of barium hydroxide and divided by the liters of the solution, which is 1.800 liters. And let's very quickly calculate how much this is. I did not calculate it beforehand, so we're gonna do this together. Divided by 171.34 divided by the 1.800, and I get here 0.19804677. Now let's very quickly look at the lowest number of sig figs. It is 4 sig figs, and it should be here. So this is the molarity, M1. And then the second step becomes very easy because we're going to plug in our first equation up here, M1V1. So I'm going to copy and paste this right here. I'm going to paste it. And then times V1, the initial volume right here is what I want to find, equals to the 0.100 molar times the 1.00 liters. All right. And in this case, I think I need to do my calculations again because there might be something that I did wrong. Let me check one more time. 61.08 divided by 171 point. Okay, so it's 61.08 divided by 171.34. All right, divided by 1.800, and I got 0.198. And then if I divide it here, if I want to determine now V1, it's going to be, so I was correct all along. I just like to check my calculations, times 1 divided by the 0.19804677, and this should give me so V1 equals to 0.5049312377. Okay, and we're sticking still with the 3 sig figs. This, note, this isn't liter, and the answer choices are milliliters, so I can say that in 1000 milliliters I have 1 liter, and then this gives me 0.5, gives me 504.9312377, and I want to round to 3 sig figs, so it becomes 505 milliliters, which is choice A. Now let's do a practice problem. This is the final practice problem of this video, and I want you to again pause your video and try to work this problem on your own. I'm trying to give a variety of problems in the video, and we can start by reading this together. It says here, a student prepared a stock solution by dissolving 20 grams of potassium hydroxide in enough water to make 150 milliliter solution. Then she took 15 milliliters of stock solution, diluted it with enough water to make 65 milliliters of a final solution. What is the concentration of KOH in this final solution? And let's see what information do I have in the question that I can extract to work this from. Okay, so let's see. So the initial concentrated solution contains 20 grams of KOH. Okay. Now, when we are working with molarity, we need the moles. So first things first, I will convert this to moles by dividing by the molar mass of KOH. Okay? Now, in 150 milliliters of solution. Now again, molarity is moles over liters, so I'll have to convert to liters. And this operation right here should give me 2.376284679 molar of potassium hydroxide. So this is the initial concentration right here. Now, and we can label this as my M1. Okay, because we're again using M1 V1 equals to M2 V2. Now, she took 15 milliliters of this stock solution and diluted it with, so 15 milliliters here becomes my M1, okay? And diluted it to make a 65 milliliters of final solution. This is V2, all right? So in this case, since now I identified all the variables of M1 V1 equals to M2 V2, and I want to find here M2, so I can say that I will take this value right here, molar, times the 15. So the volume should be in liters, okay, equals to M2, which I need to find, my variable, times the final volume, which is 65.0. Oh, this is 15.0, 65.0 milliliters. And again, I will change it to liters. Tip, you don't necessarily have to switch them over, but just for accuracy and not to confuse you, I switch them up. Therefore, when I calculate M2, this becomes 0.5483737333874 molar. And looking here at I didn't track my sig figs from here. This is 3 sig figs, and right here, all are 3 sig figs. So in this case, it becomes 0.548 molar.